Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics, Oscillators and Amplifiers. Today we are going to discuss about the amplifiers, in which the multi-stage amplifier, RC coupled amplifier and transformer coupled amplifier we are going to discuss about. In the last session we have seen the introduction about the multi-stage amplifier. So, when you see the block diagram of multi-stage amplifier, we have connected two stages. For the first stage we have given the input Vs through the source resistance Rs, and at the output of the second stage we have connected the load resistance. And why we have given two stages in the circuit is, if the output of the first stage is not enough to operate the next stage, or it is not enough to drive the next stage, then we are going for the multi-stage amplifier. Again, the output of the first stage is given as the input of the next stage to amplify. So, the signal will get amplified again by the second stage, and the output may be sufficient for driving the next stage circuits or for displaying any output signals. So, this is the basic block diagram of the multi-stage amplifier, and how the output of the first stage is connected to the input of the second stage is by three methods. One is RC coupled amplifier, that is the amplifiers, the first and second stage amplifiers are connected through the resistance and the capacitance. It is called as RC coupled amplifier. And next is through the transformer coupled amplifier. Similarly, the output of the first stage is connected through the primary winding and the secondary winding is connected to the second stage. So, through the transformer we can connect the output of the first stage to the input of the second stage, and so it is called as the transformer coupled amplifier. And without any components like R and C and like a transformer, we can connect directly the output of the first stage to the second stage, and it is called as direct coupled amplifier. This is the simple circuit diagram for the RC coupled amplifier. Consider this Q1 gives the first stage of the amplifier, and this Q2 transistor gives the second stage, and this output of the Q1 at the collector terminal is connected to the base of Q2, that is the input terminal of the transistor Q2, through the capacitor called the coupling capacitor, and this is RC. Maybe we can take this RC as the load resistance, because we are taking the output from the collector terminal. So, this terminal will give you the output to the load. So, this resistance is said to be the load resistance, considered to be the load resistance, and because of this R and C we are calling this circuit, this kind of circuit, as RC coupled amplifier. Similarly, here when you connect this output, the output of the next stage, that is the second stage, to the input of the third stage, you have to connect here a coupling capacitor, and then the output will be given as the input to the next stage. And this is the simple circuit of RC coupled amplifier. We have seen the advantages and the disadvantages of RC coupled amplifier in the previous session, and this is very less expensive and easy to use, and this gives moderate current gain and voltage gain. These are some of the characteristics of this circuit. And next is the transformer coupled amplifier. When you see the circuit diagram, TR is the transformer which is connected, the primary winding of the transformer is connected at the collector terminal of Q1, and secondary is connected to the base of Q2. So, the primary winding is considered as load of Q1, and this secondary winding acts as the input impedance of Q2. By the transformer we have coupled the output of Q1 to the input of Q2. So, this is said to be a transformer coupling amplifier, and mostly this transformer coupled amplifier is used in power amplifiers. This gives very good impedance match between the input and the output stage, and also it gives maximum power gain, and this is more expensive, so this is not commonly used in all the amplifiers. And next is direct coupling amplifier. So there is no component used between the input of the preceding stage to the output of the first stage. So it is directly coupled, the output terminal is directly coupled to the input terminal of the next stage Q2. So it is called as direct coupling. There is no such passive components or a transformer between the input and the output of the two stages, and hence it has its own drawbacks. The DC voltages will also come into effect in the next stage of the amplifier circuit. This is one of the main drawbacks of this circuit. Normally RC coupled amplifier is used in practice. We are going to see about the RC coupled amplifier and the frequency response of the RC coupled amplifier. If you want to study the frequency response, you have to give the low frequency signal, mid frequency signal and the high frequency signal. So you have to increase the signal's frequency from lower range to higher range, and you have to study the gain of the amplifier in all the frequency ranges. So if you want to study the frequency, you have to analyze the circuit in its AC equivalent model, and this is the equivalent circuit of RC coupled amplifier, and this is hybrid pi model. Here when you look at the first circuit, this is the coupling capacitor, this C suffix C is the coupling capacitor. After this comes the next stage of the RC coupled amplifier, and before this coupling capacitor is the first stage of the RC coupled amplifier. So until here you have to see all the parameters for the first stage of the amplifier, and after this coupling capacitor all are for the next stage of the amplifier. This is for Q2, and before this coupling capacitor everything is for Q1. And we know that this is common emitter configuration, since because all the parameters are having E in the suffix, and the base terminal is here, and at the collector terminal we are taking the output. So this is commonly the emitter terminal, and this is the base terminal, and here this is the source resistance in shunt with the current source. Between the base terminals it has its own internal resistance called RB dash, and this is the resistance between the base and the emitter terminal, and this is RB dash E, and you have the capacitance between any two terminals of the amplifier when you go with the frequency response or high frequency signal. So this is the capacitance effect between the base and the collector, and this is the capacitance effect between the base and the emitter, and which includes the stray capacitance also. So it is C B dash E plus C S1. And what is this resistance? This resistance is the resistance between the base and the collector, or B dash C, and this is the capacitance between base and the collector. So it is parallelly connected, C B dash C, and this is the current source GM VB dash E. And what is GM? It is the transconductance, that is the reverse of the resistance. And here this is the resistance between the collector and the emitter, or CE, and this is the capacitance between the collector and the emitter, C. This is the stray capacitance, as well as this includes the stray capacitance as well as the collector capacitance, the capacitance between the collector and the emitter. So this is given as CS2, and this is the resistance between the collector and the emitter. Otherwise you can say this is the resistance at the collector of Q1. So until here all the parameters gives the details of the first stage of amplifier, and after this coupling capacitor these are the parameters of the second stage of the amplifier. This is RB. Here this is the resistance between the base and the emitter, base RB B dash and RB dash E, and across which we have the collector between the base and the emitter. So, it is C B dash E. So, this is the entire equivalent circuit of RC coupled amplifier. So, to draw this circuit, you have to thoroughly know about how the hybrid equivalent circuit is drawn for the amplifier or for BJT circuit. We have seen in the last session. So, there are out of 4 parameters, only 2 are considered, input impedance and the output admittance. And here this is pi model, that is only hybrid model, this is pi model, this is for high frequency analysis. So, in between any 2 terminals, here the resistances are considered, in between base and collector, or in between base and emitter, or in between collector to emitter, in between any 2 parameters the resistances are considered, and so it is given as RB dash, RB dash E and RCE. And in between the base and the collector, the capacitance is also considered between base and the emitter, and also collector to the emitter. In between any 2 terminals, the capacitances are also considered, and it is given in the equivalent circuit. Here there is a current source GMVBE is given. Instead of H or E in the case of the hybrid model, here it is in the case of hybrid pi model, it is simply GMVB dash E, that is only the difference, and everything is same here for the second stage. For the second stage, we have given only the input part of the circuit, we have not taken the output side of the circuit, only input side of the circuit is considered. And these resistance and the capacitance is connected in parallel here and also connected in parallel here. We know that by Miller's theorem, if any resistor or any capacitor is connected in parallel, this can be simplified and rewritten as well as in the input side and the output side. This RB dash E is given as, in the next circuit if you see, RB dash E by 1 minus A, and A is the gain of the circuit. So, here this RB dash E is drawn as RB dash E by 1 minus A, and the capacitance between the base and the collector terminal CB dash C is given as C into 1 minus A. So, this is by the Miller's theorem. The parallel combination of this part RB dash E and CB dash C is written as this, the capacitance from base to emitter and the resistance from base to emitter. This is for the input side, and also for the output side you have to include that resistance RB dash C into A by 1 minus A, and here this is C suffix C into A minus 1 by A. Here this is simply 1 minus A, here it is A minus 1 by A is the term you have to include with the capacitance. So, this is the calculation made by the Miller's theorem, and after that when you see the circuit, everything is the same, one and the same. We have just replaced these resistance and the capacitance in parallel by the capacitance and resistance from base to emitter. These two passive components are connected in between base and the collector. Base is the input side and collector is the output side. When you give these two passive components in the input side as well as the output side, that is base to emitter and collector to emitter, this is the theorem you have to use and this is the calculation you have to make. And second circuit, that is the difference. By Miller's theorem we have replaced these two, capacitor and the emitter, from base to capacitor and the resistance between base and the collector as the same capacitor and the resistance between base to emitter as well as from collector to emitter. And in the next circuit there are assumptions made to analyze the circuit. What are the assumptions? When you compare the second circuit and the next circuit, all these capacitance is omitted and this resistance is omitted. Here also the resistance and the capacitance is omitted because the gain is very high. So, when you see here those components are omitted and the output impedance is considered as R naught here, and this capacitance is also omitted, and this is taken, this RB dash and RB dash E is taken as Ri, the input impedance of the next stage. That is the difference between the second circuit with this circuit. We will have a break now. Welcome back after the break. So, this is the simplified circuit of RC coupled amplifier we have seen by having some assumptions. Again, before this coupling capacitor there are two resistors, and after this coupling capacitor also there are two resistors. If these two resistors are taken into consideration as RC dash, that is the parallel combination of R naught RC as RC dash, and the parallel combination of RB and Ri as Ri dash. If we will take like this, you will have only two resistors here at the output side of the circuit, and this resistance is very small when you compare it with RC. Then instead of RC you can put it RC dash, you can say that it is only RC. And when you compare these two resistance, when RB is very low, you can consider only Ri. So, this circuit has Ri dash, instead of Ri dash you will have Ri in the next simplified circuit. So, in the previous circuit you have RC dash and Ri dash. Here in the next circuit, if you see, this is only RC and Ri. We have neglected the R naught here and RB here. So, this is the simplified circuit of RC coupled amplifier which is ready to analyze. In the midband frequency, we know that the capacitance effect will be very low. So, instead of these capacitance you have a short circuit here in the midband frequency analysis. There is no capacitance here, here also there is no capacitance. So, in the midband frequency if you analyze the circuit, you will have the gain as constant here. This is the frequency response of the RC coupled amplifier. The gain is very constant, and if you calculate the current gain, it is given as minus HFE into RC divided by RC plus Ri, that is the current gain, and the voltage gain, it is minus HFE into RCI by HIE, and where RCI is the parallel combination of these two resistance RC and Ri. This is the low frequency response of RC coupled amplifier. In this low frequency response, this circuit will have only the coupling capacitance, not this capacitance. The circuit in the mid frequency range, there is no capacitance in the circuit. This is the equivalent circuit of the mid frequency range. In the low frequency range, this capacitance will not come into effect, only this coupling capacitance will have some effect on the low frequency range. And so, you will have a high pass filter network here. As we discussed in the earlier, in the low frequency range of the signal, this is the response of high pass filter. Since because if you have a capacitance here, coupling capacitance here like this capacitance and this resistance, this circuit connection, this parallel connection of C and R will give you the response of the high frequency high pass filter, and this is the response of the high pass filter, and you will have a lower cutoff frequency here. So, after the lower cutoff frequency, all the signals will be passed through it, and below the lower cutoff frequency no signal will be passed through it. That is the ideal response, but normally in practice this gain will slowly increase, and once the cutoff frequency is reached, when it intersects that cutoff frequency, the gain is maximum. And for the higher range of frequency, this is negligible, that is this coupling capacitor will not come into effect, only the shunt capacitance, this will have some effect on the higher frequency range of the signal. So, this resistance in series and this capacitance in shunt, this circuit will produce a low pass filter response. So, when you see the frequency response of this RC coupled, this is the high frequency range. In high frequency range, you will have a lower cutoff frequency here. So, after this lower cutoff frequency, no signal will pass through it, and below this low frequency, all cutoff frequency, all the signal will get passed through it. This is the response for ideal case. For the practical case, the gain is slowly reduced at the rate of minus 20 dB per decade after the lower cutoff frequency. So, this is the simplified circuit, and for mid-band analysis there is no capacitance in the circuit, and for high frequency analysis only this capacitance will come into effect, and so you will have the response of high pass filter, and in low frequency analysis only this capacitance will come into effect, and so with this resistance you will have a low pass filters effect on the circuit for RC coupled amplifier, and so you will get the frequency response of RC coupled amplifier as this. So, mid frequency you have a higher gain, and for the lower frequency and for the higher frequency the gain is reduced. Now, the transformer coupled amplifier, in this circuit diagram it is given as Vs, actually it is the current source Is. Is is always shunt with the Rs, and there is a transformer here Tr1 which is connected in the input terminal of the transistor Q1, that is the secondary winding of the transformer is connected to the base of the first transistor Q1, and the load resistance of Q1 is decided by the primary winding of the second transformer Tr2. This load resistance is considered as RL1, and the input impedance of this Q1 is decided by the secondary winding of the transformer Tr2, and the load resistance of Q2, that is the second transistor, is decided by the primary winding of Tr3, that is the third transformer, and it is given as RL2, and the secondary winding of the third transformer Tr3, which is going to give the maximum power of the circuit to the load. All these transformers are selected based on the impedance match condition in the circuit, and these number of turns also to be determined by the impedance level of the circuit. If the impedance of the previous stage and the next stage is matched by these transformers, then only the output power is maximum. The maximum power can be transferred from the circuit to the output. This is the AC equivalent of that particular circuit, transformer coupled amplifier, and this Q1, the transistor Q1 is replaced by the hybrid parameters, the input impedance, output admittance HOE, and the current gain, forward transfer current gain HFE into IB. And here also the Q2 transistors input impedance we have taken into account, and that is the input part of the Q2 is only taken, and these two transistors are connected through the transformer, and here the primary winding number of turns is N1 and secondary winding number of turns is N2. This is the transformer which couples the output of the first stage Q1 to the input of the next stage Q2, and this terminal is base terminal, and this is collector terminal, and this is common emitter terminal. Similarly for Q2 transistor also base 2, emitter 2, and the collector, which we have not considered here. This is the simplified circuit of the transformer coupled amplifier. So, here we have taken the input impedance of Q2 here. The input impedance of this secondary, which affects this primary, as N1 by N2 the whole square into HIE2. That is the load impedance of the secondary which have effect on the primary of the first stage, as N1 by N2 the whole square HIE2. So, we have taken only that particular thing, and this is the impedance faced by the primary due to the impedance of the secondary, and everything is one and the same. Here the base, emitter, and this is the transistor part replaced by the hybrid parameters, and this is output voltage and output current here. We have considered this circuit as the mid band equivalent circuit, and there is no capacitance seen here. At mid frequency range the effect of the capacitors are negligible, and so this is the circuit. From this circuit, if you calculate the voltage gain, we know that the voltage gain is VB2 by VB1, and VCE1 is calculated from the circuit, and from that we have calculated what is VB2 by VB1 as N1 by N2 into HFE1 by 2. This is the current gain in the mid frequency, This is the voltage gain in the mid frequency, and this is given as typical values of the transistor. You will be getting 145 as the voltage gain, and similarly for current gain also it is 145, and both are the same value. And if you want to calculate the power gain, it is voltage gain into the current gain. This transformer coupled amplifier is mostly used in the power amplifier. So, you calculate the power gain as voltage gain into current gain. We have taken only the voltage gain calculation here, and the current gain is also easy to calculate. This is I naught divided by IB. You have to calculate what is the current I naught flowing at the collector terminal of the circuit and what is IB, and replace I naught by IB. You will be getting in terms of transformer turns ratio N1 by N2. This is in low frequency range. Only the primary winding is taken into account. There is no capacitance here in the low frequency range of the signal, and everything is one and the same. Here only the primary winding is taken, and in the low frequency we know that at resonant frequency, at the parallel combination of HOE1 and this resistance N1 by N2 the whole square into HIE2 is equal to this LP, then the higher cutoff frequency will occur. At the resonant condition, that LP is equal to the parallel combination of this admittance and this N1 by N2 the whole square HIE2, only the high frequency cutoff frequency will occur. This equivalent circuit is for low frequency range, and next is for high frequency range. In high frequency range, the series leakage inductance and these distributed capacitance between the primary and the secondary is come into effect, and the effective inductance and the capacitance, if you calculate, then it will come L is equal to L1P plus L1S into N1 by N2 the whole square, and C is equal to Cp plus Cs into N2 by N1 the whole square. At resonance, the effect of the capacitive reactance is equal to the inductive reactance. Xc is equal to Xl, and the resonant frequency will be F naught is equal to 1 by 2 pi root Lc. High frequency region, you have to say it is a lower cutoff frequency. In low frequency region, we have to call it as higher cutoff frequency. So, at resonant condition, at Xc is equal to Xl, the low frequency will occur. So, this is the simplified equivalent circuit of the transformer coupled amplifier at high frequency region. We know that L1, what is L1 and what is C. So, if these reactances are equal, then only you will have a low frequency cutoff frequency, and this is the response of the amplifier for various Q factors from 0.5 to 2. And always the gain is constant for mid frequency range and slowly increasing at the low frequency and slowly decreasing at the high frequency, and similarly for the RC coupled amplifier. So, let us summarize this session. We have seen the introduction about the multistage amplifier, and we have seen next the equivalent circuit of RC coupled amplifier at low frequency, mid frequency and high frequency, and similarly for the transformer coupled amplifier. Some questions you can try to answer for this. Why do we go for multistage amplifier? Discuss the frequency response of RC coupled amplifier and draw its equivalent circuit. Explain in detail transformer coupled amplifier in all range of frequencies. This is the reference I have used. Thank you.